Hi and welcome to this fourth video of my playlist about the best methods to reduce carboxylic esters to primary alcohols. In this presentation we'll have a look at the use of aluminum hydrides as reducing agents, mostly lithium aluminum hydride and diisobutyl aluminum hydride. These are the most expensive reagents of this playlist, but there is hardly any ester that cannot be reduced to an alcohol by lithium aluminum hydride. Unfortunately, this reagent is not very selective and will also reduce carboxylic acids, amides and even carbamates if an excess of reagent is used. Sodium aluminum hydride can be prepared from the elements at high temperature and pressure. Although it is similarly reactive as lithium aluminum hydride, its solubility is lower and lithium aluminum hydride is by far the more commonly used reagent. The latter can also be prepared in one step from lithium hydride and aluminum chloride. Thus, mixtures of sodium or lithium hydride and aluminum chloride prepared in situ may show a similar reactivity as isolated aluminum hydrides. In theory, half an equivalent of lithium aluminum hydride should be enough to reduce an ester to the alcohol. Because solvents and starting materials are never perfectly dry, though, a slight excess of hydride is usually used. Lithium aluminum hydride does not react at room temperature with dry air and is not usually pyrophoric. One may wonder why aluminum hydrides are way more powerful reducing agents than ionic hydrides such as lithium or sodium hydride. The main reason is probably the small size of hydride if compared to aluminum hydride. Hydride with a van der Waals radius of 1.34 angstrom is almost as small as fluoride, the smallest known anion. The electric field strength on the van der Waals surface of these anions is exceedingly high, and the ions in a lattice of solid fluorides or hydrides are very close to each other and held together by strong electrostatic forces. This results in a low solubility of ionic hydrides or fluorides in organic solvents. Moreover, the dissolved fraction of ionic hydride will form strong bonds to any solvent, what again lowers the nucleophilic reactivity. Just try a nucleophilic substitution with potassium fluoride. These reactions almost never work unless special solvents and completely anhydrous conditions are used. If the aluminum hydride anion is fitted into a sphere, its diameter would be around 2.5 times as large as the diameter of the hydride anion. With only one negative charge, the electric field strength on the surface of this sphere would be approximately 6 times lower than that on the surface of hydride. The consequences are an improved solubility, a weaker solvation, and ultimately a much enhanced nucleophilic reactivity. Diisobutyl aluminum hydride can be prepared by heating triisobutyl aluminum, which in turn is prepared from metallic aluminum, hydrogen, and isobutene. Dibal is a much more selective reducing agent than lithium aluminum hydride and can often be used to reduce esters to aldehydes. To completely reduce an ester, about 3 to 6 equivalents of dibal are usually used. Unlike organolithium compounds or Grignard reagents, organoaluminum compounds do not usually transfer alkyl groups to esters, ketones, or even aldehydes. Aluminum is only slightly less electronegative than zinc, and its organelles only rarely act as carbon nucleophiles. Michael additions and the transfer of allyl groups is sometimes observed, but usually no nucleophilic attack by the isobutyl groups of dibal must be feared. I'll show you now some specific examples with detailed experimental conditions. Because ester reductions usually turn alkaline, the reduction of enantiomerically pure enolizable esters, as the one in this example, can always cause partial racemization. Here, the reaction time was kept short, what helped to prevent racemization and allylic CO bond cleavage. This is an example of selective monoreduction of an unsymmetric diester. An excess of lithium aluminum hydride was used, but the reaction was conducted at -50 degrees Celsius for only 15 minutes. A high yield of the required alcohol was attained, without any isomerization of the CC double bond. Such selective monoreductions will often be easier to achieve with a diol as reducing agent, as in this example. Interestingly, here the alpha-beta unsaturated ester was reduced preferentially, probably because of its better steric accessibility. With borohydrides, the other methoxycarbonyl group closer to the amino group may have been reduced first. Symmetric diesters will be easier to reduce only once if both carbonyl groups are conjugated and thus can influence each other's reactivity, as in this example. As soon as one ester is reduced, the electrophilicity of the other carbonyl group will drop. In the second example on this slide, despite their closer proximity, both carbonyl groups influenced each other's reactivity less strongly than in the first equation, and treatment with diol gave a product mixture. Such selectivities are easier to rationalize than to predict and should always be determined with an experiment. Also in this example, a product mixture was obtained. Treatment of an alpha-chloro-beta-sulfonylamino ester with an excess of lithium aluminum hydride at room temperature gave, in addition to the expected chlorinated alcohol, a dechlorinated sulfonylaminopropanol and an etziridine, the latter formed by intramolecular nucleophilic substitution. With a smaller excess of reducing agent and at 0 degrees Celsius, the yield of the target product could be increased to 87%. Reductions with lithium aluminum hydride can even be conducted at -65 degrees Celsius, as in this example. At such low temperatures, even benzyl chlorides may remain unchanged during the reduction of an ester. Diol is also capable of reducing esters at a low temperature and thus enable highly selective reductions of polyfunctional intermediates. No double bond isomerization or allylic substitutions occurred in this instance. Examples of the preparation of iodinated alkanols from esters by reduction with diol have also been reported. Interestingly, diol does not react with dichloromethane and is often used in this solvent. Lithium aluminum hydride, however, reduces dichloromethane to methane already at low temperature and should only be used in ethers. This is another example of the reduction of a polyfunctional ester containing an iodide. Again, reduction with an excess of diol at -78 degrees Celsius proceeded with high selectivity. Also, nitriles can be reduced by aluminum hydrides, but the selective reduction of an ester in the presence of a cyano group is sometimes possible. In this example, neither the electron-deficient double bond nor the cyano group were reduced, and no racemization or alkene isomerization occurred. The reactivity of lithium aluminum hydride can also be lowered by partial alcoholysis with a precisely dosed amount of alcohol. In this example, terzbutanol was used for this purpose, and an ester was selectively reduced in the presence of an anilide. In large industrial reactors, it is often difficult to attain temperatures below -20 degrees Celsius, and a chemical deactivation may therefore be a practical strategy to enhance the selectivity of a reducing agent. Nucleophilic hydride donors may also cleave epoxides. Here, an ester containing an epoxy group was reduced selectively with lithium aluminum hydride at 0 degrees Celsius. With a larger excess of reducing agent and by conducting the reaction at room temperature for 22 hours, no epoxide but a secondary alcohol was the main product. Such epoxide reductions can, however, already occur at -78 degrees Celsius, as in this example. Again, the ring fission proceeded with high regioselectivity. Most ketones are reduced much faster than esters upon treatment with boron or aluminum hydrides. Sterically inaccessible or electronically deactivated ketones, though, may be surprisingly unreactive. In this example, it was probably steric crowding what prevented reduction of the keto group. Ketones can sometimes be protected from nucleophilic attack by enolate formation. Here, a beta-keto ester was first metallated with sodium hydride and then treated with a slight excess of alane. careful diastereoselective protonation of the enolate with terzbutanol at low temperature then yielded a hydroxymethyl ketone. Alane is less basic than ionic aluminum hydrides and can be generated by treating lithium aluminum hydride with an electrophile, for instance aluminum chloride. This reaction is analogous to the preparation of borane from sodium or lithium borohydride. This is another example of ketone protection by enolate formation. Treatment with a slight excess of LDA followed by diol at -78°C led to a primary alcohol as the main product. This example is similar to the previous one. The starting alkoxycarbonyl groups were again non-enolizable, what may have helped to improve selectivity. Aliphatic or aromatic nitro groups can be readily reduced to amines with lithium aluminum hydride. In the presence of alkoxycarbonyl groups, however, selective ester reductions are sometimes possible, as shown here. The reducing agent was partially deactivated with aluminum chloride. In this example, an alkylated malonate containing a nitrophenyl group and a chlorinated alkene was reduced selectively and in high yield. No special precautions other than a high dilution were required. Despite the excess of hydride, almost no side reactions occurred. Also, oximes can be transformed into amines with lithium aluminum hydride. This did not occur, though, in this example. A non-enolizable ethyl ester underwent clean reduction to the primary alcohol by treatment with a slight excess of lithium aluminum hydride in refluxing THF, without reduction of the oxime. So, what other side reactions do we have to expect? As mentioned, a large number of functional groups can be reduced by lithium aluminum hydride, including electron-deficient alkynes and alkenes, allylic alcohols, ketones, aldehydes, nitriles, and imines. Also alkyl and aryl halides, epoxides, carboxylic acids, and even sulfonamides can be reduced with this reagent. Occasionally, allylic alcohols will be reduced to saturated alcohols upon treatment with lithium aluminum hydride, as in this example. Also an amide was reduced here, but the protected ketone remained unchanged. Tertiary and some benzylic and allylic alcohols can also be reduced to the hydrocarbons by aluminum hydrides. Here, for instance, a pyridine dicarboxylate underwent partial deoxygenation when refluxed in ether with a large excess of lithium aluminum hydride. This could be prevented by lowering the amount of reducing agent and the reaction temperature and time. Diol sometimes reduces esters to aldehydes. This is a difficult reaction, which works best for esters with some heteroatom close to the carboxyl group. Here the reduction was conducted at -78°C for 20 minutes only, but still a partial reduction to the alcohol could not be completely prevented. Lactones are more electrophilic than non-cyclic esters and are easier to reduce just to the hemiacetal stage. In this example, such a reduction succeeded even with lithium aluminum hydride by keeping the excess of reagent and the reaction temperature low. Hydride donors such as anionic borohydrides or aluminum hydrides are potent nucleophiles that can even bring about aromatic nucleophilic substitutions. Here, a 2-alkyltiobenzothiazole underwent reductive CS bond cleavage upon treatment with lithium aluminum hydride. This here is an interesting side reaction. The intermediate aluminum alkoxides formed during the reduction of esters can apparently act as leaving group and be displaced by nucleophiles. In this example, reduction of an indanyl acetic ester gave high yields of a cyclopropane when the reduction was performed with 1 equivalent of lithium ethoxide. This additional base probably caused the deprotonation of the indane, as shown here. Without added base, however, the expected alcohol was obtained. When reducing esters with a leaving group in alpha position, occasionally unexpected products are obtained, as in this example. Such products result from the reductive ring opening of intermediate epoxides, as shown here. A lower reaction temperature and shorter reaction time may have prevented both reduction of the sulfonate and epoxide formation. Most acetals are stable toward aluminum hydrides, but occasionally acetals do undergo reductive cleavage. Treatment of the starting ester of this example with a large excess of diol at room temperature gave a benzylic ether formed by regioselective acetal cleavage. With a smaller excess of diol at -78 degrees Celsius, however, this type of acetal remained unchanged. Oximes can be reduced to hydroxylamines or amines by aluminum hydrides, but may also undergo a Beckmann-type rearrangement, as in this example. This reaction required a large excess of diol and proceeded with higher regioselectivity than the normal acid-catalyzed Beckmann rearrangement, even with the oximes of dialkyl ketones. One mechanism would proceed by reduction of the oxime to a metallated hydroxylamine, as sketched here. This side reaction again indicates that aluminum alkoxides can act as leaving groups for nucleophilic displacement. Here are some more examples, but many more have been reported. You can also copy these references from the description of this video. Esters can also be reduced to alcohols with silanes as reducing agents, and here are some references. Silanes are weak hydrolytically stable reagents suitable for reductions under acidic conditions, but are otherwise not superior to the other reagents presented in this playlist. So, to summarize, let's compare the reagents discussed in these 4 videos. Synthetic chemists contribute in 2 ways to increase mankind's prosperity. The first is by discovering new, improved compounds or materials for various applications, for instance new drugs, pesticides, explosives, or materials for batteries. The second is by finding less expensive ways to prepare known, valuable compounds or materials. That is, by finding new synthetic processes. Chemists looking for new, improved compounds will usually have to prepare many different compounds on a small laboratory scale as quickly as possible. Here, the price of reagents and the amount of waste are not a concern, and if esters must be reduced to alcohols, boron or aluminum hydrides would usually be the preferred choice. Although expensive, these reagents are easy to handle and do not require specialized equipment. The reductions usually work well even without much optimization. For large-scale industrial ester reductions, though, price and waste are decisive for success or failure. Long and tedious optimizations will be acceptable, even for tiny cost improvements. Thus, catalytic hydrogenations, ideally with heterogeneous, recoverable catalysts, are highly preferred for large-scale reductions. That's it. I hope you found this useful and stay tuned for new, in-depth videos about organic synthesis.